Hi everyone, this is Dr. Chantal Marshall once again, here to introduce you to the chi-square for test of independence. This is a follow-up to our chi-square for goodness of fit. You'll notice that the math is very similar, and we're going to use the same organization for our data that we did for the goodness of fit test. But what it is that we're testing for and how it is that we set up our expected frequencies is different for our test of independence. Since I've already set up for you what a chi-square test is, it's a non-parametric test that looks at frequencies instead of things like means and variances. I'll skip that for now since you should already know it and go pretty much just into what the chi-square test of independence is testing. One of the differences between the goodness of fit test and the test of independence is how we calculate our degrees of freedom. So I'll go into that. Then I'll talk about our new frequencies for rows and columns, which we're going to use to calculate our expected frequencies, as well as how it is that we use the formula for expected frequencies to figure out how to set up our table of data to calculate our chi-square. And of course, as I go through, I'll pull this all together into hypothesis testing so you can see all 4 steps as we're putting them together. So why would we run a chi-square test of independence? What kind of research question might we be asking? A chi-square test of independence is when you want to attempt to answer questions such as the following. Is there a relationship between religion and political party? So here we see that we have 2 different variables. One would be a person's religion as they identify it. So they may be Christian or Muslim, they may be agnostic or some other religious group. In addition, we are measuring people's political parties. So are they Republican, are they Democrat, Independent, or some other party? You'll notice that these 2 variables are categorical. They don't have numbers attached to them, and we're measuring 2 variables for each person. We can also attempt to answer questions such as, does the effect of drug type on remission depend on cancer type? So now we're looking to see if something like a type of drug and whether it works depends on the kind of cancer that a person might have. So you may have 2 different types of drugs. One works in one way, one works in another way. And perhaps you want to see if there's a difference in which drug works depending on if someone has something like breast cancer, lung cancer, pancreatic cancer, leukemia, or some other type of cancer. So here again, we see that we have 2 variables and each of them is using a nominal scale. These are categories that people are in, either drug A or drug B, and then whatever type of cancer they happen to be diagnosed with. We might also see something like this is a relationship between parents' relationship and drug use as a teenager. So for example, if parents were together while someone was growing up or not together while someone was growing up, and perhaps what kinds of drugs they tried out or used when they were a teenager. So again, we have 2 variables, each one on a categorical or nominal scale. So we can't use the type of tests that we've used before. You may think that second question reminds you a little bit of our 2-factor ANOVA. And yeah, this is actually very similar to our 2-factor ANOVA, or even a correlation since we're looking at relationships between 2 variables. But all of our variables here are categorical, which means that we have to use a chi-square test. So instead of using a chi-square test of goodness of fit, since that only worked for 1 variable, here we have to use a chi-square test of independence. And that is when you have 2 categorical variables. In order to calculate our frequencies, just what we're observing out in the world, we have to combine our variables and then tally the frequencies. So you'll actually end up with a table looking something like what our 2-factor ANOVA was showing. So For factor A or variable A, you have two different levels. For example, let's say you have two different drug types and you're looking at two different cancer types. So you may look at drug 1 and drug 2, and then here you may have breast cancer and lung cancer. And what we're going to count is simply the number of people who went into remission. In other words, they no longer have any signs of cancer in their body for each of those combinations. So in this box, we would have the people who are taking drug 1 and who have breast cancer, how many of them went into remission, and so on and so on. So we'd end up with these frequencies for the combined levels of the factors or variables that we're looking at. That means that we're now moving beyond just having columns like we did for the goodness of fit test and having rows that we have to take into account. So let's take this example of the question that we're asking in the last slide. Is there a relationship between parents' relationship, let's say they're separated or together, and drug use as a teenager? So this means that for each participant in this particular study, we're going to ask them two questions. One, were your parents separate or together when you were growing up and a teenager? And then also, what kinds of drugs did you use when you were a teenager? So again, here, we're not collecting any numbers from people. We don't want to know how many times they use drugs or, how much they might rate themselves on addicted to drugs, but simply, what kinds of drugs did you use when you were a teenager? So this starts to get us into how we might set up our hypotheses. Because we're looking for a relationship between these two variables, our null and alternative hypotheses are about the relationship. So we might say for our null hypothesis that there's no relationship between x and y, between the two variables that we have. We might also say in our null hypothesis that x and y are independent of each other. They're just two different variables that aren't related to each other in any way. That means that our alternative hypothesis is the opposite. We're saying that there is a relationship between variables x and y, and that x and y are dependent on one another. It's really up to you which of these two that you pick, either the relationship null and alternative or the independent versus dependent null and alternative. I like to use the relationship versions when I'm looking at variables that I am simply measuring. And I like to use the independent and dependent hypotheses when I'm looking at a study in which I have manipulated one of the variables. When you haven't manipulated your variables, so for example, I'm only asking people about their parents' relationships and then asking them about their drug use. I'm not forcing them to have one type of parent relationship or another, or forcing them to use some drugs. That would clearly be highly unethical. And so this is simply looking at whether there's a relationship, sort of like a correlation. But if I were looking at a manipulated variable, let's say whether a person went through DARE or not, which is a program to try and prevent people from using drugs, then I could think about them as either independent or dependent because I'm actually looking for cause and effect. Did going through a program like DARE cause people to use more or less drugs? So I'm going to go with the relationship ones because I'm only measuring these variables. So here, my null hypothesis is that there is no relationship between parents' relationship status and teenagers' drug use. And my alternative is that there is a relationship between parents' relationship status and teenage drug use. All right, so let's keep going with this question. Is there a relationship between parents' relationship status, whether they're separated or together, and drug use as a teenager? Oh, I have an extra and in there. That's okay. We know what we're talking about. So let's say that you ask 100 people what their parents' relationship status was when they were growing up and what kinds of drugs they used as a teenager. And these are the results that you get. Now, as a researcher, you get to decide about the levels for your variables. So here I've decided to take the participants who told me that their parents were together throughout their childhood and while they were growing up to be in this column, and those who said that their parents were never together or separated at some point here in the not together column. What I've then decided to do is take the participants who said they never tried any drugs or tried marijuana and put them in one level, and then put participants who used harder drugs such as cocaine or meth or heroin or ecstasy into another category. Now, you as a researcher might put these in separate categories, so maybe none could be a category, marijuana could be its own category, or hard drugs could be a third category, or you could just put none and any drug in one category, but I've chosen to put the people's answers into these two categories. Now, what you'll notice is that for participants whose parents stayed together, we have quite a few more people saying that they didn't try any drugs at all or only tried marijuana. We have fewer people saying that they used hard drugs. In the not together column, though, we have a switch. So there are more people who used hard drugs than people who didn't use any drugs at all or only used marijuana. Although this difference is pretty small, so maybe we can think of this more as just even between the two. But in either case, we have different patterns or different distributions. So in the together column, we have a distribution such that more people were in the non-marijuana category than in the hard drugs category. And in the not together column, we definitely had at least an even distribution, if not more people doing hard drugs. So what we're trying to do with a chi-square test of independence is to see if these distributions are actually different from one another. Is it the case that this pattern is very different from this pattern? If that is the case, then that means that these two are related in some way or are dependent on one another. So our chi-square test of independence is going to look at whether there's a relationship between these two variables, and that's why we're getting these different patterns or distributions within our data set. In order to test for this relationship, we need to set up our critical region, or what chi-square we need before we're willing to say that there is a relationship between these two variables. In order to do that, we need our degrees of freedom. In this particular case, we're going to take both our columns and our rows into consideration. So we take the number of columns that we have, in this case 2, subtract 1, and then the number of rows that we have, in this case 2, and subtract 1. And then we multiply those two numbers. That's what these parentheses are for. So once you have calculated C minus 1 and R minus 1, you multiply those two numbers. In this case, we have 2 columns, subtract 1, that gives us 1, and 2 rows, subtract 1, that gives us 1. So we multiply those and we get 1 degree of freedom. We're going to use our same chi-square distribution that we used for the goodness of fit test. And here we can see that if we're using an alpha of 0.05, which is the standard, and we only have 1 degree of freedom, then the chi-square that we need to get in order to reject the null hypothesis that there's no relationship between these two variables is a 3.84. So we need a chi-square above a 3.84 so that we can fall into the critical region and reject our null hypothesis that there's no relationship between these two. So how is it that we calculate our chi-square in this particular test? So this is where things get a little bit more complicated than they got for our goodness of fit test. But we're still using the same basic concept of looking at the difference between our observed frequencies, or the number in any particular category, the actual count that we got from our data collection, and our expected frequency. What is the number in each of those categories that we would expect if there was actually no relationship between these two variables? Another way that you can think about this null hypothesis is that we're saying that the distributions are the same between the levels. That would indicate that there's no relationship between these two things. In this example, we would say that the distribution of drug use is the same for those whose parents stayed together as for those whose parents did not. So however many people said they used hard drugs for when their parents stayed together, that same proportion should say that they used hard drugs among those participants whose parents did not stay together. So we're still looking at distributions and proportions of frequencies and seeing if they're the same as we would expect if the null were true. So what we need to do is figure out those actual numbers for our expected frequencies so that we can compare our observed frequency to that. So let's then look at our new formula for our expected frequencies. It's FC times FR divided by N. Now in this case, I'm going to want you to think about this slightly differently if you want to understand the proportions part. So I like to put a parenthesis around my FR over N. Now mathematically this is the exact same thing. So we can either multiply these two and then divide by N at the end, or we can figure out this proportion here, FR divided by N, and multiply that by FC. Now if that seems very confusing right now, don't worry about it. I will come back to that in just a second. What I want to do right now is introduce you to these numbers, our frequency for our columns and our frequency for our rows. We need these in order to calculate our expected frequencies. You'll notice then that our expected frequencies are based on our observed frequencies. We'll get to that as well in just a second. For now, let's look at what these FC and FR numbers are. I've gone ahead and copied the same table of data that we had in the other previous slide. I'm going to use these numbers to come up with our frequencies for each column and our frequencies for each row. So let's start with our rows. Here we have two rows, those who did no drugs or just did marijuana, and the row for those who did hard drugs. For each of these rows, I'm going to add up their frequencies, and that will be the frequency for that row. So over here on the right, I am going to add up the numbers for each row in order to come up with that row's frequency. Now, because we had 100 participants total, we need to make sure that these frequencies here also add up to 100 because you're taking into account everybody who was in your study. So if we go ahead and add across, we get 56 people total who said that they didn't do any drugs or only used marijuana. That means, therefore, that everyone else did some type of hard drug while they were a teenager. So that total is 44. You'll notice that 56 and 44 equal our 100 participants because some of them only used marijuana or didn't do any drugs, and some of them did hard drugs. So we're accounting for both of those levels in our frequency for our rows. We're going to do the same thing looking at our columns. So down here, we're going to add up all of the people who said their parents stayed together, and here we're going to add up all of the people who said their parents were not together when they were growing up. So once again, we're simply going to add. So we're going to add our 37 and our 23. That gives us 60 people total who said that their parents stayed together, and 40 people total who said that their parents did not stay together. So these are the numbers that we're going to end up using to figure out our expected frequencies. So here is what I'm talking about when I break this formula up into this formula here. What we're going to do with our expected frequencies is take into account the proportions of people that we have in each of the levels. So here's the example. We had 56 people who said that they didn't try any drugs or only tried marijuana. So that's 56% if you think about it, because we had 100 people in our sample. So if 56% of our participants said that they did not take drugs or only tried marijuana, then we would expect, if the null is true, that 56% of our sample for those who stayed together said that they didn't take drugs or only tried marijuana, and 56% of our not together group would also have not tried any drugs or only tried marijuana. So what we're doing then is saying the proportion of those who were in this level, which is 56 over 100, as you can see here, 56 over 100, and we're going to multiply that times the number of people that we actually have in that column to figure out if the null is true, then how many people should we expect in this particular group. Now, if all of that talk about proportions and seeing if they're the same between the columns seems a little overwhelming right now, that's fine. I just want you to do the math correctly. So I just want to make sure that you can use this formula when we're going to our expected frequencies. So if it's still a little bit too much right now, just go ahead and do the math, and then at some point it does click for a lot of students as they're doing the math and practicing over and over again why it is that we're doing it that way. So I just wanted to point it out, but if it's not clear right now, don't worry too much about it, but it is about the proportions being the same in the two columns. So once again, we're saying 56 people out of 100 didn't use drugs or only use marijuana. So that means if the null is true, it has no relation to whether or not your parents stayed together. We would expect 56% of the people whose parents stayed together to say this answer, as well as 56% of our not together group to say this answer. So that's what I mean by keeping the proportions the same in each of the levels, and that's if the null is true. All right, so let's go ahead then and use our observed frequencies in order to calculate our expected frequencies. So I'm just going to copy the same table we came up with in the last slide because it has all of our numbers for our frequency rows and our frequency for our rows and our frequencies for our columns, and that's what we're going to be using. When we calculate our expected frequencies, we can ignore the numbers that we actually observed. Those are unimportant for us. So I'm going to use this formula that I've gotten for the chi-square, and like I said, I like to think about it this way, where we're multiplying our proportion in each row times our total in that column, but either one is fine, and you can even try both if you want. The math will be exactly the same and it'll get you to the same answer. So then let's clear out those numbers in the middle because we don't care about those, and we're going to now calculate our expected frequencies for each of these four categories that we now have put together. So in our first box, we have those people who told us that their parents stayed together and they didn't use any drugs or only used marijuana. So what we would expect if the null is true is this number here. So we've taken our frequency in our column, which was 60, our frequency in our row, which is 56, and then divided it by our sample size, n, which is 100. When you do that math, it gives us an expected frequency in that category of 33.6. So again, we're simply taking frequency column here, putting that into our formula, frequency row here, putting that into our formula, and our n here, and putting that into our formula. And then we calculate that, and that gives us 33.6. So you can either use this formula here or this formula here. It's literally going to give you the exact same answer. So don't worry about which one you use. Now, we're going to use the same formula for each of our categories. So the none, marijuana, and not together category gives us 22.4 for our expected frequency. This is the number we should get if the null is true. Then we keep going for each category. So here we take our number in the column, 60, our number in the row, 44, and our sample size, 100. That gives us 26.4, and our last group is 17.6. You'll also notice that these numbers, these expected frequencies, must also add up to that frequency in each row and frequency in each column. So 33.6 plus 22.4 gives us 56. 26.4 plus 17.6 gives us 44, and so on. So these need to add up. You want to make sure that your expected frequencies add up to those frequencies in your rows and columns. If they don't, then somewhere the math has gone wrong. The other thing you'll notice is that once you've calculated one of them, at least when you have 4 categories, the rest sort of fall into place. So you could just calculate 33.6 and then say, well, 33.6 and this number have to add up to 60. So you can just take 60, subtract this number, it gives you 26.4. Once you have these two, then you can calculate these, because you can simply say 56 minus 33.6 gives you 22.4. So any way you want to do it is fine. If you want to just stick to the formula in each box, that works every time, so you don't have to worry about any shortcuts, and it will give you the right answer. So whichever way works better for you. Now, we're going to use the exact same formula to get our chi-square that we did for goodness of fit. So it looks like this. It's literally the exact same formula. Our FO is our observed frequency, our actual count, and our FE is that expected frequency that we just finished calculating for each of the categories. You're going to square that top. That's what makes it the square. That's what puts the square in chi-square. You'll then need to sum this for each category. So you need to do this calculation for each category. We had 4, and then add all of them at the end, and that gives you your chi-square, just like before. So this takes organization, as you all know. So we're going to use the same table that I used for goodness of fit. Once again, this is how I organize the numbers, but if it's easier for you some other way, that's fine too. So what I've done here is created a table that has all of our 4 groups that we've come up with. So I've combined them in order for each one to have its own row, so I can do the math a little bit easier. So I'm just taking the numbers that we got from our observed table and our expected table and putting them into this table so I can do the math a little bit more simply. If you want to just use another table like in the last slide, you're welcome to do that as well. I just recommend that you use some sort of organization tactic so that you can keep track of all the numbers. So here I'm simply copying the observed frequencies we got on the last slide. These are the actual counts, the actual data that we collected. Then I'm copying the expected frequencies that we calculated using that formula of FC times FR all over N. So that's that second step that we did before. And now the rest of the math is just like we've done in the past. So you're simply taking your observed frequency, subtracting your expected frequency in this column. We get some version of 3.4 for all of them, 3.4 or negative 3.4. Now you may get tempted to say, well, can't I just take 3.4 and do it 4 times and that adds up to your chi-square? And the answer is no. And that's because your expected frequencies are different for each category. And that is what you do at the end. So you don't want to just say, oh, I'll do this 4 times, because that will not give you the correct number. So here I've squared it because a negative times a negative is a positive. For all of them, it's 11.56. So here's where the difference lies. When you do this last step, you're taking this number here and dividing it by your expected frequency. So because our expected frequencies are different for each category, that means this last number on the right will be different for each category. This is what I mean by you don't just want to do it 4 times, because that's not going to give you, like you don't want to just do this top row and then multiply it by 4, because that won't give you the same answer. So here, 11.56 divided by 33.6 gives us this number, 0.344. 11.56 divided by 22.4 gives us 0.516, and so on. So 11.56 divided by 26.4 and 11.56 divided by 17.6. So these are, right, each category is contributing to the chi-square this amount. And so when you add them all together, when you sum them, that gives you your chi-square. So here our chi-square is only 1.173, which, if you remember from our critical region, does not look good. But let's put it all together into our hypothesis test. So for this particular example, we stated these hypotheses. Our null was that there's no relationship between parents' relationship and drug use. And our alternative was that there is a relationship between parents' relationship and teenage drug use. In reality, both of these should say teenage drug use. I just forgot to add the teenage on the null. Sorry about that. Here, then, our critical region was using a degree of freedom of 1 and an alpha of 0.05, which gave us a 3.84. So that we needed to get beyond that chi-square in order to reject our null. We did not get that. We got 1.173. Sad day. I don't know. Maybe it's not a sad day. I mean, if you're a parent, you probably don't hope that there's a relationship between your relationship status and drug use. So take it however you want to, but also remember that these are not real data. So in this case, we failed to reject our null hypothesis. So our p-value is greater than 0.05. So these numbers that we got, even though it looked like these distributions were slightly different between those whose parents stayed together and those whose parents did not, we just got those due to random chance or error. So there's really no relationship between these two variables. So we would say that there's no indication of a relationship between parents' relationship status and drug use. So that's what this whole test told us. So just to quickly go over the 4 steps again, when you are testing for independence using a chi-square, our null hypothesis can be stated either as no relationship between variable x and variable y, or you can say that x and y are independent. Once again, I like to use the relationship version when I'm just looking at variables I've measured, not manipulated, and I like to use the independent version when I am looking at a study in which I have manipulated one of the variables. My alternative then is that there is a relationship between variable x and variable y, or that x and y are dependent. We're going to define the critical region using these degrees of freedom, r-1 times c-1. I think this is backwards from how I had it before, but either way, the math works out fine. So you want to take your rows -1 and multiply it by your columns -1, or vice versa, but the math is the same. And step 3, you're going to calculate your chi-square using that tried and true chi-square formula that we've been given using our observed frequencies and expected frequencies. Of course, how you calculate your expected frequencies is using your row frequencies and column frequencies. So we're going to practice that so that you can get the hang of it. And then you decide, just like always, whether you reject or fail to reject your null hypothesis, and you want to state your p-value. Some reminders as you are trying to, get this all to sink in. We use frequencies or counts. So we are not using means, we're not using standard deviations, we're not using standard error, none of that. It's simply how many people did what. That we're just counting people on our fingers, and that's what we're using for our data. We are using a test of independence when we have 2 categorical variables. Now you'll notice that in these examples, I only used 2 levels for each category, but it doesn't have to only have 2 levels. For example, I could have said drug use, I'm going to categorize into 3 groups: none, marijuana, and hard drugs. And that would have given me 3 levels. So there are cases in which you have more than 2 levels for the categories, and that's where we start to get into lots and lots of categories that we are calculating. If you're only measuring, if you're only taking people as they are, you're not changing anything about them, then there's no cause and effect between the two variables. However, if you did manipulate something, so for example, if we said these students are going to go into DARE and these students are not going to go into DARE, and then we follow them for a long time and see if they use drugs, then we can start to establish cause and effect, whether or not DARE made a difference in their drug use. We're comparing, just like with goodness of fit test, observed frequencies to expected frequencies. And our expected frequencies are based on the null hypothesis. If there's no relationship between these 2 variables, and we use the proportion within the observed frequencies to calculate. So this is one of those where we need to figure out something using the data that we already have, which is very different, I know, than I think all of our other tests that we have done in this class. So if you're still having a hard time wrapping your head around it, it's okay. This stuff can be a little bit hard to understand first go around. So this is why you should practice and read your chapters and go through all the practice problems in the book, etc., etc. And these, of course, can be decimals. So your expected frequencies can be decimals. Your observed frequencies cannot, because you're counting people into one specific category. And we use the same 4-step hypothesis testing that we've used in the past. So hopefully now you understand the difference between a chi-square test for goodness of fit and a chi-square test for independence, and that you're starting to think about practicing so that you can get those expected frequencies and put everything into a nice organized table or something that can help you keep track of all of the data, and that you hopefully see the value in using a chi-square test so that we can actually collect data using categorical variables and not everything has to be a number, and still be able to show something important about our participants and of course about people. So thanks for watching and good luck practicing.